Good morning. This is your stats sensei, Mr. Spensei, and we're going to go over a warm up on central limit theorem and the normal distribution as a combination. So the mean household income in the U.S. is highly skewed to the right with a mean of 105,000 and the standard deviation of $90,000, and that's approximately right. And the reason it's skewed to the right is because you can make $0, and some people make billions, not many, but some. So that skews it out to the right. And we're going to say that the mean is $105,000. And actually, the median is about 76,000. So you can see that it's definitely stretched to the right. So we have a mean of 105 and a standard deviation of 90,000. And a random sample of 81 households is taken. Draw a graph illustrating empirical rule for the distribution of means. You must show 3 standard deviations above and below the mean. You must clearly label the z-scores and actual values. So it's the distribution of the means. So we need to discuss what the conditions are. Well, we have to have a random sample, check. And even though it's skewed, we can still use a normal for the distribution of means if our sample size is greater than 30. And so in this case, n equals 81, which is greater than 30. So it's approximately normal by CLT, by central limit theorem. And I'm just going to abbreviate CLT. So in this particular case, we have a mean of 105,000. Well, let's start off with our z-scores because the z-score part's still going to be the same, 0, 1, 2, 3. Now, keeping in mind the underlying distribution, the distribution of the actual income is skewed, and we said it's highly skewed to the right. However, the distribution of the means becomes normal or approximately normal if we have a sample size greater than 30, and in this case, we do. So we have 105,000. And let's go ahead and remind ourselves that this is still 68%, 95%, and 99.7%. All right. So that's where we're at. But we're changing by we have n equals 81. Well, the distribution of the population has a standard deviation of 90,000. So standard deviation is 90,000 for the population, but we're not interested in that because we're working with the distribution of means. And the distribution of means is the standard deviation of x bar, which is the standard deviation of the population divided by the square root of n. And in this case, it's 90,000 divided by the square root of 81. So 90, 1, 2, 3, divided by the square root of 81. And we end up getting $10,000 because it's essentially 90,000 divided by 9, which equals 10,000. So the standard deviation of x bar is 10,000. So this means everywhere we have, this is 10,000, this is 10,000, and this is 10,000. This is 10,000, 10,000, and 10,000. All right. Well, that means if we're changing by 10,000, this is 105, this is 115,000. This is 125,000. This is 135,000. Over here, 95,000, 85,000, and 75,000. So there's that's the distribution of the means, and I'm going to call it that because this is distribution. It is not involved with the actual set. The actual data set is skewed to the right, but the distribution of means is normal by central limit theorem. So a random sample of 25 households is taken. Can you use the sampling distribution of means to calculate the probability that the mean household income of the 25 households is more than 120,000? So can you use the sampling distribution of the means? All right, to use the normal distribution or the sampling distribution of the means, our sample size, since it's skewed, we can't because our sample size is less than 30. So it says, justify your response and describe the sampling distribution of means for the group of 25. All right, calculate the probability if it's appropriate to do so. Well, that's not appropriate. So no, we cannot use CLT or the distribution of means because the distribution is skewed and n equals 25, which is less than 30. All right, so that's why we can't use it. It did ask to describe the sampling distribution. Well, the mean is the mean is the mean, so the mean is still 105,000. And they want the distribution of the sampling means. Well, the distribution of the sampling means, regardless of the sample size, we'll have to use this formula. The standard deviation of X bar is the standard deviation of the population divided by the square root of n, which in this case is 90,000 over the square root of 25. Well, this because that was our sample size. So this is 90,000. Square root of 25 is just 5. And if I take my calculator and go 90, 1, 2, 3, divided by 5, I get 18,000. So that's the standard deviation of X bar. In the shape, we're going to keep the shape easy. The shape is not normal. Matter of fact, we're going to add one other thing, still skewed. It's not as skewed, but it's still skewed. So it's not normal. Number 3, a random sample of 25 households is taken. Can you use the sampling distribution of means to calculate the probability that the mean household income of 36 households is more than 120,000? Oops, this says 25. This should say 36. So let's scratch that out and make it 36. So now we're working with 36 households. Well, in that case, we can justify your response. We can use CLT because n equals 36, which is greater than 30. So that takes care of our normality problem. So in this case, it says, justify your response and describe the sampling distribution of the means. So the distribution of the means, the mean is the mean is the mean. So the mean equals 105,000. The standard deviation, well, the standard deviation of X bar is the standard deviation of the population divided by the square root of n. So in this case, it's 120,000 divided by the square root of 36. So that's 120,000 divided by 6. And if we do that, we find out that that makes it, oh, not 120,000, excuse me, 90,000. Sorry about that, 90,000. 90,000 divided by 6 equals 15,000. All right. It also asks us to calculate the probability if we can. In this case, we can. So we're going to go ahead and draw our normal distribution. So our normal distribution is centered at the 120,000. That's our mean. And we want to know the 105,000. I'm having a little bit of trouble. Let me start over with that. Matter of fact, I'm going to put this on a card since I kind of ran out of room. So our center, our mean is a mean is a mean. So our mean is 105,000. We want to know the likelihood of getting 120,000 or more, which means this goes to positive infinity. So we're going to go to the calculator and we're going to use z-test. And it's going to ask us for our mean. Well, our mean is 120,000. Then it's going to ask for the standard deviation of the population. Standard deviation of the population is 90,000. It's going to ask you for the X bar, which is the average, which in this case, I'm still doing this, the mean is 105,000. The X bar is 120,000. Our sample size, in this case, was 36. And it's going to ask us the direction of shade, and we're going to shade to the right. So hopefully I don't mess this up again. So we're going to go stat, test, z-test. Make sure stats is highlighted. We wanted a sample size of a mean of 105,000, standard deviation of the population of 90,000, a sample mean or X bar of 120,000, a sample size of 36, and we needed to shade to the right for a greater than and press enter. Make sure you have that selected and press enter, then press calculate. And we find out that it's 0.1586. So the probability that a household group, a group of households has an average of more than 120,000, a group of 36 households have an average of more than 120,000 is about 16%. So not common, but not completely unusual. I appreciate you watching, and I hope to see you on the next one. Thank you.